Today we are going to find the non-relativistic limit of Klein-Gordon equation. We can write the total energy of a relativistic particle as sum of rest mass energy and relativistic energy. For very small velocities, this relativistic energy E dash is actually the kinetic energy. If E dash is only the kinetic energy, then this E dash is very small compared to the rest mass energy. So we can write E dash is very less than the total energy. This symbol is E dash is negligible. This is called the relativistic limit. Let us write the free particle wave function as a product of a relativistic part and a non-relativistic part. Here phi is the relativistic part and the exponential part is non-relativistic, and also it is independent of the spatial coordinates. Let us see explicitly what is actually mean by the relativistic part and the non-relativistic part. If the energy operator acts on psi, that gives the total energy E. If the energy operator acts on the relativistic part phi, that gives the relativistic energy E dash. And that's why phi is called the relativistic part. If the energy operator acts on the exponential part, that gives the rest mass energy m0 c square. So it's called non-relativistic part. What happens if the energy operator acts on this equation? Let's operate the LHS and RHS with the energy operators. We can use the product rule for the derivatives to do that. At first, let's put phi outside and operate energy operator on the exponential part. Then let's put the exponential part outside and operate the energy operator on phi. IH cross dou phi by dou t. Let me separate this action of energy operator with a red color. This is actually phi times m0 c square times the exponential part plus the exponential part m0 c square t times E dash phi. Let's club together the phi and the exponential part as shown, and this gives actually m0 c square psi plus E dash psi, which is equal to m0 c square plus E dash times psi. If you take a close look, this is actually E times psi. So we can write E times psi is equal to m0 c square plus E dash times psi. This gives E is equal to m0 c square plus E dash. This is actually the total energy of the particle. This implies we can actually separate the free particle wave function into a relativistic and a non-relativistic part. Let me write it one more time. The free particle wave function psi, which is equal to a relativistic part phi of rt times an exponential part e to the power minus I by h cross m0 c square t. Let me ask you, what's our target? Our target is to find the non-relativistic limit of Klein-Gordon equation. For that, at first, we need to find the second derivative of the free particle wave function psi with respect to time. Then we need to find the non-relativistic limit of this second derivative of the wave function with respect to time by putting E dash is equal to 0. Then simply substitute this value of dou square psi by dou t square in the Klein-Gordon equation. Gives the non-relativistic limit of Klein-Gordon equation. Clearly, this non-relativistic limit of Klein-Gordon equation be some type of non-relativistic quantum mechanical equation. Maybe it may be the Schrodinger equation. Just keep this wide guess in your mind. For finding the second derivative, at first let's find the first derivative. Just apply the product rule and you get the answer. Let me do it. 5 times e to the power minus I by h cross m0 c square t times minus I by h cross m0 c square plus e to the power minus I by h cross m0 c square t times dou phi by dou t. Let me take the exponential part common, that gives dou phi by dou t minus I by h cross m0 c square phi times the exponential part e to the power minus I by h cross m0 c square t. Using this equation, let us find the second derivative of psi. Simply just applying the product rule to this equation gives the second derivative of psi also. Let me do it. E to the power minus I by h cross m0 c square t times dou by dou t of dou phi by dou t minus I over h cross m0 c square phi minus I by h cross m0 c square times e to the power minus I by h cross m0 c square t bracket dou phi by dou t minus I by h cross m0 c square phi. Let me rub this. Let us simplify the second derivative of psi with respect to time a little more. Let's take the exponential part as common outside the bracket. After that, let me take this time derivative inside. This gives dou square phi by dou t square. And this time derivative on this gives minus I by h cross m0 c square dou phi by dou t. This on this gives minus I by h cross m0 c square dou phi by dou t. This on this gives 1 by h cross times 1 by h cross is 1 by h cross square minus into minus plus I into I minus 1. So this is actually minus 1 by h cross square m0 square c to the power 4 phi. You can simply see that the second and third terms are same. So you can simply club it together. So we can write this expression as e to the power minus I by h cross m0 c square t times dou square phi by dou t square. I write it with reading purposefully, so keep it in mind. 2I by h cross m0 c square dou phi by dou t minus 1 by h cross square m0 square c to the power 4 phi. Let us find what is that red term or dou square phi by dou t square. For that, let me first act the energy operator 2 times on the relativistic part of the wave function phi. The first bracket is actually E dash phi. So we can write this as the energy operator acts on E dash phi. So this is actually I h cross dou by dou t operates on E dash phi. Let me rub it. We can write this expression as I h cross dou by dou t of I h cross dou phi by dou t. Let me take this E dash outside. So this gives E dash I h cross dou phi by dou t. Let me multiply the i's and the h crosses in the LHS separately. This gives minus h cross square dou square phi by dou t square is equal to, this is actually e dash times phi. So this is equal to e dash square times phi. From this expression, you can simply find dou square phi by dou t square is equal to minus e dash square by h cross square times phi. We already learned about the non-relativistic limit, and we know that in the non-relativistic limit, the relativistic energy E dash is very small as compared to the total energy E. So this implies the E dash is negligible. So this implies the dou square phi by dou t square also negligible. So we can take this dou square phi by dou t square is equal to 0 in our expressions. So this makes the dou square phi by dou t square in dou square psi by dou t square vanish. So let us write it more explicitly. So dou square psi by dou t square is equal to e to the power minus I by h cross m0 c square t times minus 2I by h cross m0 c square dou phi by dou t minus 1 by h cross square m0 square c to the power 4 phi. Let me take this minus sign outside the bracket. So this becomes plus and the minus sign comes outside. This is one of the most important step. So let me mark it with a red ink. Now we have the non-relativistic limit of the second derivative of the free particle wave function with respect to time in our hand. Our task is to substitute this non-relativistic second derivative in the Klein-Gordon equation, and that gives the non-relativistic limit of the Klein-Gordon equation. We all know that the Klein-Gordon equation is dou square psi by c square dou t square minus del square psi plus m0 square c square over h cross square psi is equal to 0. Let's substitute this dou square psi by dou t square here. Let me put the minus sign outside. So this gives minus 1 by c square 2I by h cross m0 c square dou phi by dou t plus 1 by h cross square m0 square c to the power 4 phi times our exponential part e to the power minus I by h cross m0 c square t minus del square psi. We know that the psi is e to the power minus I by h cross m0 c square t times the phi. You already know that this del square or the Laplacian only acts on the special part. So you can take this time dependent part outside the operator. So we can write this as del square phi e to the power minus I by h cross m0 c square t. Let me give a vector symbol over this del to denote it's a spatial operator. Plus m0 square c square over h cross square e to the power minus I by h cross m0 c square t times phi equal to 0. Let me take this c square inside the bracket. This gives m0 c to the power 0 m0 square c square. As a next step, let me take the exponential part common from this whole equation. As a next step, let me take a minus sign and the exponential part common from this whole equation. This gives minus common. So minus times 2I by h cross m0 dou phi by dou t plus 1 by h cross square m0 square c square phi plus del square phi minus m0 square c square over h cross square 5 times e to the power minus I by h cross m0 c square t is equal to 0. The RHS is 0, so I can take this exponential part to the RHS and can cancel it. So let me rub this exponential part. No need of it. And also the second term and this fourth terms are same. So I can cancel it. Let me rub this all and write this del square phi just above. Let's multiply this whole equation with minus h cross square over 2m0. On doing so, you can simply see that the second term become the kinetic energy operator, and also you can see that the first term become the energy operator. So this equation is equivalent to minus h cross square over 2m0 del square phi minus I h cross dou phi by dou t is equal to 0. And this is equivalent to minus h cross square over 2m0 del square phi is equal to I h cross dou phi by dou t. And this is actually the Schrodinger equation. Schrodinger equation for the free particle, because there is no potential term here. So we can say that the non-relativistic limit of Klein-Gordon equation is actually the Schrodinger equation. And this non-relativistic limit is the limit where the relativistic energy is very small compared to the total energy E, and this implies the relativistic energy E dash is negligible, and this happens only at the velocity of the particle is very small compared to the velocity of light.